Hi everyone, we will solve the ninth worksheet today. So let's start. It's about the graphs. So we will determine whether the graphs are directed or undirected, have directed or undirected edges, or multiple edges, or loops. Okay. So what's a directed edge or undirected edge? So here's sorry about it. So here's a little small notations. So the edges that look like this are called directed, and that look like this are called undirected. And from a vertex to other vertex, if there are more than one edges, we say it's multigraph. Okay. And if from a vertex to another there are both directed and undirected edges, we say mixed graph. Okay. So for the first graph, we see there is no edges that look like this, so it's undirected. Okay. And we see between two vertices there is only one edge, so we say it has no multiple edges. And we don't see something like this. There is no edge which starts with a point and ends with the same point, so there is no loops here. Okay, so it's undirected, no multiple edges, and no loops. Okay, and what about B? Here we have this graph. We see it's again undirected, okay, because all edges look like this, okay. And for example, from D to B or from B to D, there is no direction, so we can say each of that. So there are two edges between B and D. And for example, between A and B, there are two edges too. So it has multiple edges, okay? And there is loops. There are loops, for example, for A, B, and D. There are three loops, so it has loops, okay? For C, here we see all edges is directed, right? So it is directed. And what about multiple edge? We see there is only, for example, between C and D, there are more than one edge because we see, for example, this and this. So it has multiple edges, okay? And there's, of course, loop. So for example, for E and C, there are two loops, so it has loops. And what about this? It's undirected, right? There is no directed edges, so it's undirected, and it has multiple edges because here we see between B and D and A and C, there are multiple edges, and there are no loops, okay? So here we have the answers, okay? Okay, for the second question, we will find the number of the vertices, edges, okay, and the degree of each edge, each vertex. So let's start with the first one here. So we see we have the vertices A, B, C, D, and E. So we have five vertices, okay, 5 many. What about the edges? So let's start. Sorry. So here we see. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. Okay, so we have 13 edges. as in here, it's 13. Okay, and now we need to find all degrees of the each vertices. So each vertex, sorry. For example, for A, so remember that if we have an undirected graph, then we compute edges as 1. If we have some line, some edge look like this, we compute it as +1. And if we have some loop, we add 2, okay, for the degree. But if it's undirected, okay. So for example, for A, we have 2 plus 4y. We have an undirected graph. So here we have a loop, which is 2, okay, which contributes 2 to the degree of A. Here we have 2 for this loop. And we have 1, 2, 3, 4 edges. So for each of them, we add 1, so we have 4. Thus, the degree of A is 6. What about the degree of B? We have 1, 2, 3, 4, 5, 6 edge, right? So it's 6. And what about E? The degree of E is 3, right? 1, 2, 3. And what about D? Degree of D is, here we have 3, 4, 5. Okay, it's 5. And what about C? Here we have 3, 4 edges here. So for each of them, we add 1. So we have 4 plus for this loop, we add 2. So it's 6. Okay. So for A, we have 6. For B, we have 6. For E, we have 3. For D, we have 5. And for C, we have 6. Okay. Okay. Now, what about this? We need to compute. So the number of edges and vertices are homework for you. Okay, let's talk about the degrees. For example, for degree of A, we have 1, 2, 3 many edges, right? It's 3. And what about degree of D, for example? There is no edge, right, around this D, so it's 0. Okay. What about degree of F? Again, there is no edge around it, so it's 0. Okay. The only different things are these D and F from this graph. So the remaining part is homework for you. Okay. And here you can see the answers. Okay. Okay, so let's skip 3. Now we will find the in degree and out degree, okay, of each vertex. So if we have a directed graph, we call in degree and out degree for separate the degree of the edges actually of the vertices. So what's in degree? It's the edges that comes through to the vertex. Okay. For example, for A, we have this loop. For these graphs, by the way, if we have a loop, we add only 1, okay, not 2. So here we have, for A, for example, we have 1, 2, and 3. We have 3 edges that ends with A. So the in degree of A is 3. Okay, we denote it by this negative, okay, degree negative of A. Okay, so I'm passing the numbers of the edges and the vertices. They are so clear. So let's talk about these degrees. Okay, so what about B? We have only one edge which ends with B, so the degree of B is 1. What about C? We have this edge that comes to C and this one, so degree of C in degree of C is 2. And what about D? There is only one edge which comes to D, so it's 1. Okay, now what about odd degrees? Okay, let's compute that too. So what about A? And for odd degrees, we denote them degree plus A of A. Okay. Again, for if we have a loop, we add only one. Okay, so we have one loop plus, and there is no other edge which starts with A, right? So there is only one edge there. So the degree of A, odd degree of A is 1, as in here. Okay. So what about B? There are two edges right here, and there are two edges which starts with B, right? So the odd degree of B is 2. What about C? It's only this edge starts with C, so we have 1. And what about D? We have this edge, and this one, so it's 3. Okay, so the answer is here. Okay, if you want to check again. Okay, so B is homework for you also. Okay, so for this part we will decide if the given graph is bipartite. So let me recall you some theorem from the lecture. So it says G is bipartite if and only if it's possible to paint the vertices using the colors, 2 colors only, okay, such that adjacent vertices have different colors. So we will exactly use this because otherwise it's so hard to determine. So for example, let's use only green and red, okay, to color the vertices. So first of all, you need to, of course, know the definition. We say it's bipartite if and only if. So we have here this theorem, but the definition of that is here. So we need to separate this vertex set of the given graph into 2 vertex sets, okay, such that any of 2 vertices here are connected, or in other words, there is no edge between any 2 of vertices here, and it holds for this set too. Okay, so so we have this theorem too. Okay, we will apply that, and at the end we will check if we have the definition or not, if the definition holds or not. Okay, so let's start first by painting the colors, the vertices, sorry. So let's paint this by this green. Okay, then remember, if we have adjacent vertices, they should have different colors. So these are, as there is an edge between them, this B and E are neighbors. So we need to color that with a different color. Okay. So again, for A and E, we see they are neighbors, so we need to paint it with another color too. And for C and D, we have the same situation. So what are the vertices, the sets of vertices? So first vertex set is V1. We will call it V1. Okay, and let's write it as this. So it contains only the vertices with green. Okay, so which is E only. And what about V2? It is A, the other ones, the red ones, A, B, C, and D. So of course there is no two pair of vertices, so we don't need to check that. What about this? If we take any 2 points from this vertex, any 2 vertices, okay, from this set, they are not neighbors because there is no edge between them, right? For example, if we take it A and B, there is no edge between them, so they are not adjacent, they are not neighbors. And for example, if we take A and C, again, we see they are not neighbors. So any two pairs that we choose from this vertex set, V2, this pair, this pair which is formed by two vertices that are not neighbors, okay? So this graph is bipartite, okay? So how do we conclude that? We first paint the vertices and see the two vertex sets, okay? And check if any two pair is neighbor or not, okay? Okay, here we have the answer clearly. Now let's check C. We will again use colors. So for example, start with F. You can start whatever you want, okay? Wherever you want to. So F, we started with F. We see A and F are neighbors, so we need to paint it with red. And for E, again, because F and E are neighbors. And we see F and D are neighbors too. So we need to paint it with red too. Okay, and for B, again, we see its neighbor of F, so we paint it with red. And what about C? C is neighbor with B and D, okay, and also A and also E, so we need to paint it with red. We need to paint it, okay, with green. So what are the vertex sets? So V1 is, let's again write the green ones. So it's F and C, and V2 is A, B, E, and D, right? So let's check. For example, for V1, we have only one pair, F and C. So are they neighbors? No, there is no edge between them, so they are not neighbors. So this holds the property that we want. What about V2? Let's check A and B, for example. A and B, there are no edges between them. right? A and E, again, there is no edge, no edge, no edge, right? What about E and B? There is no edge like this, right? So they are not neighbors to either. And A and D, again, they are not neighbors. Okay, so it holds. So this is also bipartite. Okay, here you can see the answer clearly. Okay, let's look at 7. We will find the degree sequences, okay, for each of the graph in exercise 6. So I found for A and C. Okay, let's look at them. So what's the degree sequence? First, you need to enumerate first the vertices. So A, B, C, D, E. So not enumerate, but order. You need to order them, okay? So we will write the sequence with respect to this order, okay? So what's the degree of A? There's only one vertex, one edge, sorry, so it's 1. What about degree of B? Again, it's here, 1. What about degree of C? It's 1. And degree of D, again, we have only one edge, so it's 1. And degree of E, there is 1, 2, 3, and 4. There's 4 edge, so it's 4. Okay. Now, what's degree sequence? So we start with A, it's 1. Okay. And then we have B, its degrees. 1, sorry. So we have 1, and C, we have 1, 1, and 4. Okay. This is the degree sequence, okay, of this graph. Okay. So here we have I made a mistake there, so it's 4 here. This is not 2. This should be 4. Okay. Okay. Now let's clear and compute the second one, the C. So again, we will order A, B, C, D, E, F. Okay. Now what's the degree of A? It's 2. B, 2. C, 1, 2, 3, 4. Okay, and D is 2, 2, and 4 again. So what's the sequence? We start with A, 2, B, 2, C, 4, D, 2, E, 2, F, 4. So this is the degree sequence of this graph. So here we have 2, 2, 4, 2, 2, 4. Okay. So, okay. You see, I didn't make a mistake here. So let's clear. Now, so we suppose first that we have this degree sequence, okay? We will compute the number of the edges of this graph, then we will draw it, okay? So for that, we will use some theorem, which is called handshaking theorem. So it says if you have some graph, okay, with the set of edges and set of vertices, which is undirected, okay, and which has m many edges, okay, you have such graph. Then it says you have this equality 2 times m is equal to the sum of the degrees of the vertices, okay? So we will use that. as we have this sequence, okay, which is formed by the degrees of the vertices, okay? So on the right, we have this summation, 5 plus 2 plus da da da, which gives us 14, okay? So on the right, we have 14. Now, then we have 2m equals to 14, which implies m equals to 7. And remember, m represents the number of the edges. So this graph, which has this degree sequence, has 7 edges. Okay. Now the only thing we need to do is to draw the graph. So we start, we know there are how many vertices? We have 1, 2, 3, 4, 5, 6. We need to have 6 vertices. So first I note them, okay? V1, V2, V3. This is V2. This one is V2, okay? First I note them, okay? 4, 5, 6. Then what do? We know the first vertex, which is V1, has degree 5, so there should be 5 edges, okay? So there should be 5 edges, okay? Then the second vertex, which is V2, should have 2 edges. So one of them is this, and we don't know the other one yet, okay? So one of them should be this. And the other ones should have this many. Each of them has 2 edges. So let's first draw this. You know these ones already, right? We have 5 many edges. So we know the last one, which is V6, has only 1 edge. So we're done with it, okay? And the other ones should have 2 edges. Now, if we write like this, then this V4 will have 3 edges, right? So we cannot directly draw like this. So what if we we erase it? Okay, so we have now this. Now V2 has 2 edges, V3 has 2 edges as we desired here, and V4 has only 1 edge because so this is clear now, okay? Only 1 edge and 1 edge. Now these should have 2 edges both, so we connect them and we're done, okay? We just need to try, so. Now the question 9. Represent the graph in the first exercise with adjacency matrix. So here we have this. We will write its matrix. What do? We first write the vertices in order. Okay, so we will write the vertices. Now, after writing these vertices, we need to check if we have an edge or not. Okay, for example, between A and A, do we have an edge? If we have an edge, if we write here 1, then it means we have a loop there. Okay, so as we don't have a loop, we write 0. Okay, and what about B and A? Do we have an edge between them? Yes, we have only one edge, so we write 1. And between A and C, so I made a mistake there too. Between A and C, we have again edge, so we write 1. And between A and D, we don't have any edge, right? So we write 0. And what about A and B? Again, we said we have one edge and there is no loop, so we have 0 there. And between C and D, there are edges between B, so we have ones here. Okay, and what about C? We have an edge between A, so we have 1 there. And C and B, we have again an edge. We have 1. C and C, there is no edge. So we write, there's no loop actually. We write 0. And C and D, we again write 0. And A and D, there is no edge, 0. B and D, there is only one edge, so we write 1. And C and D and D and D, there is no edge, so we write 0. Okay, there is only one mistake here, 1, it should be 1. Okay, the other ones are homework for you. You see it's clear already. So what about 10? Okay, oh, we are given now the matrix. Okay, so we will try to draw the graph. So we have this. We first note the vertices. Okay, we have A, B, and C. Here we see we don't have any loop because on the diagonal we have zeros. So we have no loops. So we see that we have B and A, there is one edge. You should know that, okay. So here we see we have 1, then it should be one edge. And we see A and B, we have again 1, so there is only one edge there. Okay, so we read actually this matrix to get the number of the edges between the vertices. So for example, between C and B, we have only one edge, and there is no edge between A and C, right here. So the graph should be like this. And we will again draw the graph, which is represented by this matrix. So we see the numbers except 1 and zeros, right? So it means there are multi-edges. So between A and A, it means there is a loop. We have a loop here, as in here. So for this, we have this loop. Okay, and for this, again, we have a loop there. Okay. And for this number 2, between A and B, we see we have 2 edges. So we have these ones. And so we have only, we had all edges there, okay? And between C and B, we have 3. So these are 3 edges between them. And here we see again 3 there. Okay, sorry, it should be with the same color, sorry. So here we have 3. What about D? D and A has only one edge, as in here, and as in here too. And the remaining one is C and D. I guess there is only one edge between them, and finally we have this. Okay. Now 12. We now use the incidence matrix, okay, to represent the graph. We will use the graph in the 6th exercise. So here we have, we will only find this one. Like, no, both of them, A and C. So here we have these this graph. Now for incidence matrix, we first enumerate the edges, okay? So for this edge between A and E, we say we call it E1. Okay, between B and E, we call it E2, ta ta ta. So we have here on the left, we write the vertices, and here above, we write the edges. Now what do we have? So we have one there. There's E1, which connects A with to some another vertex. So we have one there, and there is no B is not a starting point or ending point of E1. So there's 0, 0, 0, and finally for E, it connects E and A, so we have one there, okay? And similarly, we write for E2, so E2 connects B and E, so we have only ones for them, and the remaining parts will be 0, okay? And for E3, we have ones for C and E because it connects C and E. Okay, and the remainder will be 0, and similarly we write ones for D and E for E4. Okay. And what about this one? Now we again enumerate the edges. So, and write them above of the matrix, and on the left we write the vertices. So for E1, we see it connects C and A. So for A and C, we write ones, and the remaining one will be 0. So what about E2? It connects A and F here. So A and F. And what about E3? Here we have E3. So we have the vertices E and F, okay? E and F. And E4, which is here, which connects C and E, okay? C and E. So I guess you get the point. For the last time, we write for E5, which connects F and D. Here we have F and D. Okay, we fill the remaining parts similarly. So here we have incidence matrix, okay, of this graph. Now this is the last question. So we found that, okay, this is the last question. So we will determine if the given two graphs are isomorphic or not. So here we have the definition. We say they are isomorphic if we can find a bijection between them. A bijection is a function which is one-to-one and onto, okay? And this bijection should satisfy this property, okay? If A and B are adjacent or are neighbors, then their image should be neighbors too, okay? So, but if you can, I guess, imagine that it's a little bit hard to decide if the given two graphs are isomorphic or not. So there are some theorems which are so useful to decide if the given ones are isomorphic or not. First of all, you need to check if the given two graphs satisfy these conditions. First of all, if they are isomorphic, then their the cardinalities, the number of the elements of the vertex sets should be equal, and the set of edges, also the number of the set of edges also should be equal, okay? and their degree sequences should be equal. Okay, so let's say you check all of them and you don't see any difference. Okay, then you try to find a bijection which satisfies this. Okay, so you write a bijection um, according to the degrees of the elements. Okay, so then you will check if the adjacent matrices are equal or not. Okay, so for this example, we see that, for example, U1, so first I named that, the vertices, I named them, okay? Oh, we have already names, okay, so first of all, you check if the degrees, if there is a vertex which is different from the other ones. So we see all of them has degree 2, right? And here again, all vertices have degree 2, right? So we can consider, we can imagine like there may be a bijection between them, okay? Because it seems there is no difference between them, right? All both have 5 vertices and the number of the edges are the same, right? So we will try to find a bijection, okay? Now here I said, for example, I sent U1 to V1, okay? This was random, okay? I choose one of the vertices here. Okay, I choose V1. Okay, so send U1 to V1. Now what do? We see the image of U1 here, image of U1 equals to V1. So what about, we will decide U2, right? So we don't know yet this part. We will decide U2. So what was the property? Here we have, we know here U1 and U2 are neighbors, as in here. U1 and U2 are neighbors. Then f of U1 and f of U2 are should be neighbors too for this graph, okay? So we need to pick an element from here for the image of U2, which is a neighbor of V1, okay? So what are the neighbors of V1? So here we have some edge and another edge, and that's all. These are two neighbors of V1. So for example, if we pick V2, okay, then we see U1 and U2 are neighbors here, and f of U1 is V1 here, f of U2 will be U2, and they are not neighbors. So the function f will not satisfy that property, so we cannot choose V2, okay? That's why I'm trying to find some vertex which is neighbor of V1. Okay, let's choose V3 here, as in here, V3. I'm sorry. So here we see U1 and U2 are neighbors, and f of U1, which is V1, and f of U2, which is V3, are neighbors too. Okay. Now what do? We will choose a vertex from here for U2. Okay. Then we need to check the vertices that are neighbors of U2. Okay. So U2 are connected with them. Okay. U2 and U4. We said U2 is V3. Okay. We're looking for f of U3. So U2 is a neighbor of, U2 is a neighbor of U3. So their image should be neighbors. So the image of U2 is V3. So what are the neighbors of V3? This and this, and this. But we cannot choose V1 because it's the image of U1 and we want F to be a bijection. In particular, we want it to be injective, one-to-one. So we cannot choose V1 for that. So the remaining vertex is V5. So we choose V5 there. Okay, similarly, we complete the rest and get this function. Now, we see it's clearly a bijection, right? It's one-to-one and surjective, okay? So the only thing we need to check if this function satisfies that property, this property. Okay, you say we have only 5 many vertices. It's not that hard, but we have some theorem which is so useful. So let's use that. Maybe in the exam you will have some graph which will have so many vertices. So let's use that. It says that if so we need to check the matrices, the adjacency matrices, okay? So for the first graph, we write here, we have U1, U2, ta, ta, ta. We have this matrix, okay? Clearly, there is no loop. The diagonal will be zeros, will have zeros, okay? And there is an edge between U1 and U2 and U1 and U5. So we'll have one there, one there. So for U2, we'll have one. For U5, we'll have one. So we have some column like this, okay? And similarly, we fill the rest, okay? So first, for the first graph, we have this matrix. Okay, for the second, we reorder these vertices according to this function, okay, f. So we have v1, then v3, as in here, then v5 here, v2, and v4. And similarly, we order them here, okay, then we check. So there is no loop again, so diagonal will be 0, and there is an edge between v1 and v3, okay, here v3, we have one, and v1 and v4. v4 is in here. And similarly, we complete the rest. For example, for v1 and v3, we have one, and v5 and v3, we have one, okay, as in here. So we complete the rest and we see they are exactly the same matrices. So it says that this function, this bijection satisfies this property. So it says we can conclude that these two graphs are isomorphic under this function, okay? So you can easily check by using these matrices if the function that you construct is a bijection which satisfies this property or not, okay? So the rest is homework for you. If you have any question, you can attend the office hour, which is on Fridays between 5 and 7 p.m., okay? So that's all for this week. See you.